Okay, now let's discuss about the consequences of Kepler's second law. To discuss it, let's consider this diagram. Here S is the sun, C, A, D, E, A prime, F are the different positions of a planet. Let's say where A is the point on the major axis nearest from the sun, and A prime is the point on the major axis farthest from the sun, and this nearest from the sun, it is called perihelion. And when the planets are farthest from the sun, that point is called aphelion. Now the point near A, the planet moves a distance c to d in a time t, let's say, and near the point A prime, that is near the aphelion, the planet moves from the point E to F in the same time t. Now the arcs CD and EF being small in comparison with the planet's distance from the sun, they may be taken to be straight lines. So I am drawing that figure to here. Here it is the sun, here it is the point C, here it is the point D, and this is the smallest distance, that is the perihelion, and here it is the aphelion A prime, and here it is the point F, and here it is the point E. Now when compared to the distance SA, CD can be very small, so this can be considered to be straight line. If CD is a straight line, then if you form this one, this area can be treated to be a straight line, a triangle. So now according to Kepler's second law, this areas SCD will be equal to the area SEF, that is, this is the area SEF. So since this CD and EF are considered to be straight lines, we can write the expression for the area of SCD as half into SA into CD. Similarly for SEF, the area is given by half into SA prime into EF. But we know that this distance SA is less than SA prime. Then if this is smaller, and then for this expression to be valid, this CD should be greater, or we can say that CD is greater than EF, which implies that that is, if CD is greater than EF, they covers, or the planet covers these distances in same time, then we can say that this CD is larger, means the velocity of the planet at this position is greater, or we can say that the velocity of the planet during the perihelion is greatest, and the velocity of the planet is least during the aphelion. So that is one of the greatest consequences of the Kepler's laws of planetary motion. That is, when the planet is near to the sun, it moves very fast, and when the planet is farthest from the sun, it moves with the less speed or least velocity. So as the planet approaches the sun, its velocity increases, and as the planet moves away from the sun, its velocity decreases. That is one of the consequences of the Kepler's law. And the important thing which we have to note here is that the velocity of the planet is greatest during the perihelion, and the velocity of the planet is least during the aphelion. In between this perihelion and aphelion, the velocity will be varying, depends upon the distance from the sun. Now if you consider the third law, actually it says that square of the time period of the planet is proportional to the cube of the semi-major axis. Then this law can be used to find a planet's average distance from the sun compared to the Earth's average distance of 1 astronomical unit. Here I am introducing a new unit, 1 astronomical unit. We will define this astronomical unit on the fourth unit of while discussing the stellar astronomy. But here the definition for 1 astronomical unit is the distance between the Earth and Sun is called 1 astronomical unit, and its value is exactly 1.496 into 10 raised to 11 meters. Now in comparison with this distance, we can find the average distance of other planets, all other planets, that is the 7 other planets in the solar system, by knowing their period. By observations we can determine the period of oscillation, period of revolution of a planet around the sun. Then if we represent the period in years p, then Kepler's law can be written in this way: d cube is equal to p square, where d is the average distance of the planet from the sun and p is the period of revolution of the planet around the sun. Now we can, if we consider dE as the Earth's distance, then dE cube is proportional to PE square, that is Earth's period. And if you consider a planet whose distance is, let's say, dP, then dP cube is proportional to P square. Now if we divide these two equations, then we will get P square divided by PE square, period of Earth, is equal to dE cube divided by dP cube divided by dE cube, which implies PP square, that is the period of the square of the period of a planet is equal to dP cube divided by dE cube into PE square, where PE is the period of Earth's revolution round the sun, which we know that 1 year, and dE is 1 astronomical unit, the distance of the Earth from the sun. If we substitute it here, we will get pp square is equal to dp cube, or pp means the period of the planet. If you generalize it as p, then p square is equal to d cube, the distance, average distance of the planet in years, where this d should be in astronomical unit, where d should be in astronomical units. So there is another consequence of Kepler's planetary motion, laws of planetary motion. Now we will discuss the verification of Kepler's first law, how we can verify the Kepler's first law in case of Earth. If you consider the case of Earth, it is verified that the relative path of the Sun is an ellipse, so that the path of the Earth round the Sun is also an ellipse. That means when we observe the relative path of the Sun around Earth, you can see that it is an ellipsoidal or in elliptical in path. Then we can say that it is a relative motion. Since we are on Earth, we are observing that, or we are experiencing that Sun is revolving around the Earth. But the actual thing is that if it appears that the Sun is revolving in an elliptical orbit around Sun, the actual thing will be Earth is revolving around the Sun in an elliptical orbit. Another thing is that if you consider the angular diameter of the Sun, that means if you consider the size of the Earth, that is the angular diameter, the actual, we can observe the Sun as a circular object, and if you consider the distances of between these 2 points, two diametrically opposite points, it is called the angular diameter, and it is actually the angle subtended by the two extreme ends or diametrically end points at the eye on the Earth, which is called the angular diameter, which is greatest about around December 31 and which is least about July 1. That means the angular diameter of the Sun is varying, and it is least during July 1, means the Sun is farthest from the Earth. That is the, if when compared to the Earth, this term is named as the perigee. So farthest from the Sun, it is called apogee, and the angular diameter is greatest when the Sun is nearest to the Earth, and which is called perigee. So the distance of the Sun from Earth varies in between this apogee and perigee, which is the evidence for elliptical orbit of the Earth around the Sun. The term perigee means when Sun's distance from the Earth is least, and apogee means Sun's distance from the Earth is greatest. When distance is greatest, then the angular diameter will be small. When the distance is least, the angular diameter will be greatest. And these terms perigee and apogee is used in reference with the Earth. If you are using the Earth as a reference, then the objects nearest to Earth is called in the position of perigee, and when they are farthest from the earth, then that position is referred to as apogee. But the perihelion and aphelion is on the basis of sun. When an object is nearest to the sun, which is called perihelion. When the object is farthest from the sun, it is called aphelion. So don't confuse with this perigee, apogee, and perihelion and aphelion. Perihelion and aphelion is used in reference with the sun, and perigee and apogee is used in reference with the earth. Okay, now we have to discuss about the how we can calculate the dates, that is time on earth, that we will discuss in the next lecture. Thank you.